Welcome to this explainer. When we look out at the vast, churning ocean, it's pretty easy to just focus on the water itself. But today, we're going to look way past those waves and travel all the way down to the bottom. We're looking at the sea floor, but not as some lifeless layer of muck. We're looking at it as Earth's ultimate time capsule. It's basically a massive planetary hard drive, and this hard drive is incredibly thick. In some places, it's holding millions of years of data, stacked up meter by meter, just waiting for us to read it.
So what lies hidden down in those deepest trenches? Well, imagine a continuous, non-stop data stream of tiny particles falling into the abyss, day after day for millions upon millions of years. This slow, silent snowfall is actually recording the rich history of our planet's climate, its biology, and its geology. Every single grain that settles in the dark down there tells a very specific story of what the Earth looked like high above the surface.
But to start, we really need to define exactly what this planetary data is made of before we scan the depths. Marine sediments are, at their core, mineral and organic particles that have been removed from their original locations by air, water, or ice, and have eventually settled to accumulate on the seafloor. Think of wind blowing dust, rivers washing mud, or massive glaciers dropping gravel. The margins of our continents and the deep ocean floor are just constantly receiving this massive, unending supply of particles.
All right, moving to Section 1, System Check the 4 origins of ocean data. Just like you'd organize files on a computer, scientists have a whole high-tech indexing system for this based on origin. The absolutely crucial thing to remember here is that every single particle on the ocean floor falls into one of 4 specific categories. We've got lithogenous sediments derived from land, biogenous coming from living creatures, hydrogenous precipitating right out of the water, and cosmogenous literally arriving from outer space.
Let's break down that raw data, starting with the first 2. Lithogenous materials, things like quartz sand and clays, are produced by the weathering and erosion of rocks on land. So picture fierce winds, raging rivers, and melting glaciers actively pushing dirt into the sea. Biogenesis sediments, on the other hand, come from the hard parts of marine organisms that just don't degrade when they die. This includes the incredibly detailed microscopic shells of algae and protozoans that live way up in the sunlit surface waters. Then we have this slightly rarer stuff. Hydrogenous data consists of minerals precipitating directly out of seawater due to chemical reactions. This creates fascinating formations like manganese nodules that just naturally scatter across the abyssal plains. And finally, cosmogenous sediments. Yep, our ocean floor is sprinkled with actual space dust. Iron-nickel spherules and tiny meteorites are constantly drifting down from the cosmos and mixing right into the marine environment. How cool is that?
Okay, Section 2, the data crunch, the physics of sinking.
So we know where the data comes from, but how does it actually get deposited across the globe? Well, it all comes down to a really counterintuitive fact about physics. You'd naturally think the absolute smallest particles would be the easiest to move, right? Actually, no, because microscopic clay particles are flat and incredibly cohesive, meaning they stick together like the wet pages of a book. It takes much higher energy, much faster currents to erode them than it does to move larger, loose grains of sand.
To make sense of this, oceanographers use something called the Hillstrom curve. Think of it as a visual readout for this massive sorting algorithm. It charts the exact relationship between how fast water is moving and the size of the particle it can erode, transport, or drop. And because of these strict physical rules, the mean grain size of sediment you find in any particular area of the ocean is actually a direct historical record of the ocean's energy at the exact time it was deposited. Fast water leaves big grains, still water leaves tiny ones. And get this, here is a truly staggering number for you. Theoretically, a single microscopic clay particle is so incredibly tiny that it could take 50 years to settle 4 kilometers down to the ocean floor. Half a century. Just imagine a speck of dust floating through the dark water column for decades before finally coming to rest.
But nature actually has a high-speed data transfer method. I mean, how do these tiny particles reach the bottom in roughly the same area they were formed if it takes 50 years? The answer is biological compression. Nearly all biogenic sediment particles are eaten by small animals and bundles into fecal pellets. This essentially compresses the microscopic shells together, causing them to sink so much faster, reaching the ocean floor in just a few days instead of decades.
Moving right along to Section 3, microscopic scams, biogenesis, and the CCD.
Let's zoom in on those biological records, specifically areas where the seafloor is made of over 30% biogenic material, which we call oozes. The brilliant little architects of these oozes come in two main flavors. We have organisms like Ch04s that build calcium carbonate shells, which contribute to calcareous oozes. And then we have organisms like diatoms, which build these beautifully intricate glass-like silica shells that create siliceous oozes. The life cycle that builds an ooze is pretty straightforward, but it happens on a massive scale. First, a huge biomass of these shell-producing microorganisms blooms up in the sunlit surface waters, areas of really high productivity. When they die, their shells sink. Finally, an ooze forms on the seafloor. But here's the kicker. It only forms if the shells rain down faster than the ocean water can dissolve them. It's kind of like snow accumulating on a slightly warm sidewalk. It only piles up if it falls fast enough.
Now, there is a major catch for those calcium carbonate shells. There's this invisible acid shield deep in the ocean called the calcite compensation depth, or the CCD. It sits at a depth of about 4.5 kilometers. Down there, the conditions, specifically the lower temperatures, higher pressure, and lower pH, cause calcite to dissolve. So as these calcareous shells sink below this invisible line, they literally dissolve away into the water, completely erasing that part of the hard drive.
Because of this invisible boundary, calcareous oozes rarely survive in the absolute deepest ocean basins. High calcium carbonate content strongly correlates with the shallower peaks of mid-ocean ridges. Why? Because those underwater mountains rise up above the calcite compensation depth. This chemical barrier completely alters the geological data we find, depending entirely on the depth of the seafloor.
Which brings us to our final section, Section 4, Satellite Readout, Mapping Global Sediment Distribution. Let's pull back from the microscopic details and chemical constraints for a second and look at the macro satellite readouts of our global sediment distribution. It's fascinating. The coarse, land-based, neritic deposits hug the coastlines really closely. Meanwhile, out in the vast, deep stretches of the open ocean, those pelagic zones, the seafloor is dominated by ultra-fine abyssal clays and those sprawling fields of biogenic oozes we just talked about. And when we look at sediment thickness across the globe, it's wild. We see massive accumulations, sometimes tens of thousands of meters thick, piling up along passive continental shelves, especially near major river mouths. But then look at the mid-ocean ridges. Because that seafloor crust is newly formed by cooling magma, the sediment layers there are incredibly thin. They only gradually thicken as the ocean floor ages and moves outward, away from the ridge over millions of years. So as we wrap up this explainer, I really want you to consider this. For billions of years, the ocean has faithfully recorded the Earth's history through dust, dissolved minerals, and microscopic shells. But right now, we're adding new, unprecedented materials into our oceans at a rapid pace. How is our own human impact eventually going to settle into this ancient, ongoing data stream? When future scientists pull a sediment core from our current era, millions of years from now, what exactly are they going to find?